Welcome to the third episode in our 5G waveform series, where we're diving into one of the most critical steps in 5G communication, cell search. In this video, you'll learn how user equipment detects a cell using the primary and secondary synchronization signals. We'll break down how it synchronizes in time and frequency, estimates carrier frequency offset, and determines the physical cell ID. Then we'll move into MATLAB, where we'll write and run receiver code that loads the 5G waveform, performs frequency synchronization, including subcarrier offset and CFO estimation, applies time synchronization, and finally calculates the physical cell ID. Let's get started. Cell search is the process by which a UE identifies a cell before any actual data connection is established. This involves three key steps: detecting the presence of a cell, synchronizing in both time and frequency, and identifying its identity. To support this, 5G cells periodically transmit two key signals within the synchronization signal block. The primary synchronization signal is transmitted in the first symbol of the SSB and spans 127 subcarriers. It's used for initial frequency estimation and symbol timing synchronization. The secondary synchronization signal is transmitted in the third symbol of the SSB, also across 127 subcarriers, and carries information used to determine the cell's identity. Both PSS and SSS are built using M sequences, which are binary signals taking values of -1 and +1, similar to BPSK modulation. The PSS can take on three possible options, while the SSS supports 336 unique combinations. By detecting and decoding both signals, the UE can compute the physical cell ID using the formula shown on the slide. During initial access, the UE searches for the PSS using correlation. It compares the received signal with three known reference sequences. If a correlation peak appears for any of them, it indicates that the corresponding PSS is present in the signal. The index of this peak is also used to determine the time offset to the slot where the SSB is located. Frequency synchronization follows a similar approach. Since the SSB may be shifted from the carrier frequency, as explained in an earlier video, we perform a blind search by applying all possible frequency shifts from the GSC and raster to the received signal. Each frequency-shifted version of the signal is then correlated with the known reference sequences. The version that yields the highest correlation peak indicates the subcarrier offset of the SSB from the carrier frequency. However, the subcarrier offset isn't the only factor affecting the SSB's frequency position. Another important factor is the carrier frequency offset, which must also be estimated and corrected. In 5G systems, signals are initially generated at baseband, meaning they are centered around 0 Hz. Before transmission, they are upconverted to the desired carrier frequency. However, due to imperfections in the oscillators, the actual frequency used may slightly deviate from the intended carrier, causing a misalignment between the signal's spectral center and the carrier frequency. On the receiver side, a similar down-conversion process brings the signal back to baseband. But once again, oscillator imperfections can introduce additional errors. The result is a shift between the expected baseband center and the actual center of the received signal spectrum. This shift is what we call carrier frequency offset. The CFO can be estimated in a similar way to the subcarrier offset using correlation. Alternatively, it can be estimated by leveraging a property of the 5G OFDM waveform, the presence of cyclic prefixes. These prefixes are repeated portions of the symbol placed at its beginning. This repetition enables detection of phase changes within a symbol, which can be used to estimate the CFO. We'll explain this process in more detail in the next part of the video. In the second part of this video, we'll demonstrate a MATLAB-based receiver implementation that performs frequency and time synchronization and calculates the physical cell ID. We'll be working with a 5G downlink waveform that contains two synchronization signal bursts, each consisting of 4 SSBs generated in the previous episode of this series. If you haven't seen that video yet, we recommend watching it first or downloading the corresponding code using the link provided below. We begin the receiver implementation with the parameter setup starting with the carrier frequency. Next, we define the subcarrier spacing used for the SSB and the sampling frequency, both in Hertz. These values must match the characteristics of the recorded waveform to ensure correct processing. Then, we load the previously generated 5G signal and assign it to the variable Rx waveform. Using the defined sampling frequency and subcarrier spacing, we calculate the number of subcarriers. Finally, we determine the maximum system bandwidth based on the sampling rate using a utility function that follows the 3GPP specifications. Next, we visualize the received signal by plotting its spectrum and spectrogram, which helps us inspect its frequency content and time frequency characteristics. As expected, the loaded waveform contains 2 synchronization signal bursts, each with 4 SSBs, transmitted at a 20 millisecond period. Now let's move on to frequency synchronization using the PSS signal. We start by defining the OFDM parameters for the SSB. First, we set the number of subcarriers to 256, the smallest power of 2 size, that can fully contain the 240 subcarriers used by the SSB. Next, we calculate the sample rate and define the number of resource blocks, which is always 20 for SSBs. Using these parameters, we generate the OFDM information object. With that ready, we move on to building the reference grid used for correlation with the received signal. We begin by defining the subcarrier indices occupied by the PSS, which range from 57 to 183. Then, we create a reference grid with 2 OFDM symbols, leaving the first one empty. This is done to account for longer cyclic prefixes that may appear in the first symbol of some slots. Next, we perform PSS detection using a correlation-based approach. We begin by looping over a range of possible frequency offsets, applying each shift to the received waveform using a complex exponential. To do this, we first define a time vector that matches the waveform length. In the next step, we downsample the waveform to match the SSB sampling rate. This significantly reduces the computational complexity of the correlation. We then loop through all possible NID2 values, which are 0, 1, and 2, and generate the corresponding PSS sequences. For each combination of frequency shift and NID2, we compute the correlation between the reference grid and the downsampled received waveform. To perform this step, we use the NR timing estimate function, which returns the timing offset, measured in samples to the correlation peak, as well as the correlation values between the input waveform and the reference grid, which in our case contains the PSS. The peak value of the correlation function, along with its index, indicates a potential PSS position in the signal. Since the PSS is located in the second symbol of the reference grid, we adjust the index by delaying it by 1 symbol. To keep track of these results for all frequency offsets and NID2 combinations, we define the appropriate storage variables before entering the loops. Finally, we identify the combination that produces the highest correlation peak. This reveals both the coarse frequency offset and the corresponding NID2 value. We then convert the frequency offset from hertz into subcarrier spacing units. In the receiver script, we now move on to the next step, subcarrier offset and CFO detection. First, we compute all possible SSB frequency raster positions, as explained in the SSB video. We then apply the PSS frequency synchronization function to estimate the frequency offset of the received signal. In the absence of CFO, this value directly reveals the SSB subcarrier offset. However, if CFO is present, we select the raster point that is closest to the estimated offset. After identifying the best match, we frequency shift the received signal to center the SSB in the spectrum. Finally, we visualize the correlation values and display the detected subcarrier offset and NID2. The highest peak on the plot corresponds to NID2 equals 2 and a frequency offset of -17, which matches the exact values we configured in the transmitter implementation from the previous video. These values are also displayed in the console output for verification. Now, let's simulate a simple channel with a CFO of 1.3 subcarrier spacings. We apply this offset by shifting the signal using a complex exponential function based on the defined CFO value. To ensure accurate detection, we expand our search range by adding extra frequency shift candidates around the known raster positions. After running the detection, we calculate the estimated CFO by subtracting the SSB subcarrier offset from the overall detected frequency offset. This value is also printed in the console. As shown in the output, the SSB offset is still correctly detected as -17, and the estimated CFO is 1.5, which is the closest candidate to the actual 1.3 spacing offset we introduced. While we could improve accuracy by adding more CFO candidates, this would increase computational complexity significantly. Instead, a better approach for fine-grained CFO estimation is to use the cyclic prefixes, which can detect fractional CFO values more efficiently. In the PSS frequency synchronization function, We begin by applying the previously estimated coarse frequency offset and downsampling the received waveform to match the SSB sampling rate. We then estimate the fine frequency offset using a custom function where we pass in the downsampled waveform at the estimated SSB position. Finally, the total CFO is computed by adding the fine offset to the earlier coarse estimate. Inside the fractional CFO estimation function, we first define the OFDM parameters. We extract the number of samples in the short cyclic prefix, determine the number of subcarriers, and calculate the symbol length in samples. The key idea is to detect phase shifts caused by CFO by comparing the cyclic prefix to its matching portion at the end of the symbol. To do this, we delay the signal by NFT samples and multiply it element-wise with the conjugate of the delayed signal. Since individual samples can be noisy or affected by fading, we sum the correlation over the CP length, which smooths out the noise and strengthens the CFO signature. Because each SSB contains 4 OFDM symbols, we repeat this process for all 4 and sum the results, further enhancing the estimate's robustness. Finally, we compute the angle of the summed correlation, which gives us the phase shift due to CFO. We convert this phase from radians to hertz, scaled by the subcarrier spacing, to obtain the fine frequency offset. As a result, the displayed CFO value is close to the expected 1.3, indicating that the SSB is ready for further decoding after frequency correction. In the next part of the video, we demonstrate timing correction. For this, we use a custom PSS timing offset function, which returns the number of samples to the slot containing the SSB. An additional parameter, threshold PSS, is introduced and used within this function to determine correlation peaks. Timing synchronization is similar to frequency synchronization and is also performed using correlation. Therefore, we again create a reference grid with 2 symbols. The first symbol is empty, and the second is occupied by the PSS. This reference grid is then correlated with the received signal. We assume that each correlation peak above the defined threshold indicates the presence of a PSS in the signal. However, these peaks may span several samples due to distortion around the actual peak. To isolate a single peak sample, we use the Get Best Timing Offsets helper function, which ensures that only the highest correlation sample within each peak region is selected. In the receiver code, we process each SSB in the signal. First, we extract it using a custom extract function. This function applies OFDM demodulation to the received waveform, adjusted by the estimated timing offset of the current SSB. We then extract the SSB from the OFDM grid. Since our reference grid for timing estimation left the first symbol empty, the actual SSB occupies symbols 2 through 5 in the demodulated grid. Next, we detect NID1 and the physical cell ID. The SSS detection process is similar to that of the PSS. First, we extract the signal from the current SSB. Then, for each possible NID1 value, we calculate the corresponding cell ID, generate a reference sequence, and perform correlation with the extracted SSS. The detected NID1 is the one that corresponds to the highest correlation peak. Using this, we compute the final physical cell ID. As shown in the console output, the detected NID1 and cell ID values are printed for each of the 8 SSBs present in our 5G signal. These values match the ones set in the transmitter configuration in one of our previous videos. And that wraps up this video. If you'd like to dive deeper into 5G cell search, be sure to check out the next episode in the series, where we explore the physical broadcast channel and the master information block. Thanks for watching.